1 over S, okay, u minus w, because, well, the plant is 1 over S, and we have modeled the disturbance as a w, u minus w, so this becomes basically 1 over S, u is r minus y over tau, r by tau minus y over tau minus w, right? I'm just substituting for u from there, which is just the, this is from the control rule. And this is just from these, this is just from the plant model. And then we're just substituting over here, and we rearrange this, and it's easy to show. You can rearrange this to get y equals r over 1 plus s tau minus w over s 1 plus s tau. Okay, this is just rearranging this equation to get this. Okay, so we have now got what the output is as a function of the command r and as the function of the disturbance w. So to study what how the system behaves, we do basically what we did for the second order system, okay, or the first order system, which is that we're going to give it a step input and see what happens, okay. And the standard way of doing this is to basically ignore the disturbance, okay, just say disturbance goes away. In our case, we are studying the input. What this really means is that we're studying a system where the web server has stopped working. It's just not doing any work, and we want to see what happens in the step input, okay, because that's how we study the response. So in this case, we said w equals 0, that goes away, and then r is going to be equal to 1 over s, because the Laplace transform of u of t, so Laplace transform of a unit step is 1 over s. And so we get y equals 1 over s, 1 plus s tau, okay. And we can write this using partial fractions as 1 over s minus 1 over s plus 1 by tau. And this in the time domain gives you yt equals 1 minus e to the minus t by tau. So in the text there's a minus sign missing. It should be 1 minus e to the minus t by tau. And if you remember this is basically the same thing over here. In fact, it's a first order system, so it's the asymptotic rise like so, and it goes to 1, okay. It's exactly a first order system, that we saw earlier with in fact the time constant tau, okay. So what we've seen is that the web server system modeled in this way with the plant 1 over s and the control given as u is equal to r minus y over tau is just a straightforward first order system, and so we get the equation. That's why I said studying first order system is useful, because in this case I actually arranged things to be this way that the web server is a first order system. Okay, and any questions about this over here? Yeah.
So why doesn't return to r after time tau here? It seems to me.
Why doesn't return to?
You're saying that after time tau, we want the y.
We would like to get there, but in fact with this particular control we won't get there. We'll get there asymptotically. We'll get to only 60% of it, right? So and this is the way that's what the math tells us, that we won't actually get there even though we want to. And so we yeah, that's just the way it works out. Okay, what you are saying is we want to get identically to 1 after time tau, but we're not going to do that. We actually, if it turns out, we're going to get that asymptotically to tau to 1, because the input is step 1, right? So we're going to get to it.
But there's like, I don't know, like we have supposed there's no disturbance, so.
Beg your pardon? There's no disturbance, correct?
But still, it's not reaching the.
It's not reaching there with this particular control rule. No, it's not reaching there. You can think of it this way. What's happening is that as you start giving more input, the error is diminishing. Okay, you give it some input rate. Remember, there's no delay, so the error diminishes. So my proportionality goes down. So it diminishes again, right? So as I approach this, the error keeps decreasing and decreasing and decreasing, so my control keeps decreasing and decreasing. I'm always trying to get there tau later. But because the error keeps decreasing, I'm not actually giving it at the rate that I started at the beginning. My input is going to actually also, it's not going to be sent at this rate. In fact, the input is going to be, it's going to be declining like so. It's going to be asymptotically declining as well, right? So that's what's going on. So I'm saying get to this buffer set point value with the error, but when I approach it, the error diminishes. So my control is going to back off. I approach even closer, it diminishes. So I'm always going to have slight amount of error, slight amount of control. Okay. We can look at the steady state error by looking at the final value of E. And unfortunately there's a typo here as well. So we want to look at lim t tends to infinity E of t, and we can find that using the final value theorem as the limit s tends to 0 of SE, which is going to be the limit s tends to 0 of s 1 minus y. 1 because it's a step input, and actually, am I doing this right? Okay. So, and that becomes s tends to 0, and this is where the mistake is. It's s 1 minus 1 over s plus 1 over s plus 1 by tau. And so this basically is going to be minus 1, because this becomes s, and that becomes s over s plus 1 over tau. In the text, one of the terms is missing. It should be, it says s minus s over s whatever. So this is what it should be. So, and then that turns minus 1. The issue is that basically we have a persistent error, and so yeah, we have a problem. Okay. Yeah. Yeah, actually, I'm just thinking in the transform domain unit step. I think should be 1 over s minus y. Right, but that doesn't look correct because the yeah, I think I get a 0 error over here, but typically in proportional mode you have a, yeah, okay, this actually you're right, because the transform of u is 1 over s, so this should be 1 over s. Yeah, okay, yeah, I think I'm making a mistake over here. This definitely is another typo. Okay, another change over here, so because the Laplace of u is 1 over s, not 1 over s. So the limiting error actually becomes 0, because in the asymptotically we're going to approach a unit step. Okay, in this case we don't have persistent droop. Typically we will have a droop. Okay, let me actually do this for the homework problem, which is a little bit complicated. Okay, did everybody get this? I made a mistake over there. So it should not have been 1 minus y. It should be s times 1 over s minus y. And then if you do the final value, you'll find that the limit is going to be 0. Yeah?
So in that equation, y equal, like the term that we cross out, not that it matters, but I think it should be w tau over 1 plus s tau. So
Is it? Oh, that's right. I'm sorry. Yeah, there should be. Okay. When you rearrange it, did I leave the? Okay. Okay, it's possible.
But it will be 0.
Yeah, it will be 0 anyway. But I'll double check that. Thank you. W tau. Okay. All right. Yeah. Okay. Yeah, it goes away anyway. So, reason for typos is that I did everything on a sheets of paper, wrote it all out, and then I transcribed it into FrameMaker. And some of the times I was transcribing it, I was tired. Let's put it. I wasn't paying as much attention as I should have, and I have been over this 2 more times, but I just Yeah, it's hard to, I guess I just didn't find it, and 3 reviewers looked at it and they also didn't find the mistake. So now I have 34 reviewers. So, and I'm going over it very carefully, so I'm finding these mistakes. That's one reason to teach it, I guess. None of these are fatal typos, but it's annoying anyway, and sorry about that. Okay, let me now do the homework problem and then we'll take a break. So in the homework problem, I said that the plant is given by 1 over s plus alpha. And so what happens over here is that the plant, we actually have a similar situation, except y goes 1 over s plus alpha times u minus w. And then when you rearrange things, we get it gets a bit more complicated. So I'm going to actually, so I'll just show you here. You have actually basically just have s plus alpha. And then if we ignore the w, which we can, what we'll get is that y, sorry, let me just write down the final thing, because this is what you should be looking at. Y equals 1 over tau s plus alpha plus 1 over tau. Okay, so this should be the intermediate step you'll get for y. Okay, and as you'll see, when alpha is 0, which is what you had in the book, you'll get exactly 1 plus s tau.
So what is the value of tau?
Because tau is the same as mu. I'm sorry. When Piazza for some reason doesn't like tau, it likes mu. So I'll put in mu over here just to make sure you guys aren't confused. So mu. Okay. When I put in backslash tau, it gets it just ignores it. Yes. I spelled what wrong? T-A-O? T-A-O. Oh. Ah, sure. That's right. I'm thinking of Zen. And and this is Greek. No wonder. Tau. I'm enlightened. Okay. Thanks. I was scratching my head for a long time saying, how could it be it just doesn't like my tau? Okay. Yes.
What is the value of r you're taking?
1 over s for step input.
Okay, so the s also comes in the denominator, right?
Yeah, but this is just y right now. Oh, sorry, r over, I'm sorry, yeah. Okay, yeah, it'll come in the denominator. So when we expand, when we expand this, we get basically for r equals 1 over s, we get y equals 1 over, I'll just use mu, I guess, 1 over mu, and I'll do the partial fraction like so. A over s plus b over s plus alpha plus 1 over mu. Okay, so this is going to be the partial fraction, because the this 1 over mu comes out, and then I have r equals 1 over s, so it becomes 1 over s, and then the other term is s plus alpha plus 1 over mu, so I can certainly write this as a over s plus b over s plus alpha plus 1 over mu, okay, because those are the two terms. And then I have a equals limit s tends to minus alpha plus 1 over tau. It will be 1 over s, so this is going to be minus 1 over alpha, sorry, 1 over mu, sorry, alpha plus 1 over mu. Okay, and then b is going to be, I'll just tell you what it is. B is going to be, wait a minute, a is, am I doing this right? It's s plus, right? So 1, it should be positive, not negative. So how did I get that? Actually, let me do it this way. Okay, I should follow my notes instead of trying to wing it. So it's going to be 1 over mu. Let me just write it like this, it will become clear. 1 over alpha plus 1 over mu over s minus 1 over alpha plus 1 over mu over s plus alpha plus 1 over mu. Okay, so this is the partial fraction expansion, and you can see that because if you multiply this by this, you get basically s over alpha plus 1 over mu plus 1, and you get minus s over alpha plus 1 over mu. So the s and the minus s cancel out, you're just left with 1, and so you get this as the partial fraction expansion. And then this can be written as yt equals 1 over 1 plus alpha mu minus 1 over 1 plus alpha mu e to the minus alpha plus 1 over mu t. Okay, so that's the final answer for yt. So you can just check your work. So you should be getting this yt equals 1 over 1 plus alpha mu, which is the constant, minus 1 minus 1 more alpha mu e to the minus 1 alpha plus 1 over mu t. Okay, so I checked my work here like 20 times, so I'm pretty sure it's true. Okay, so did most people get this? Or and then the other question was, what is the gain? So I accidentally, somebody asked me, by gain do you mean Kp? And I said yes, and actually I should distinguish between loop gain and the system gain. It's actually two different things, and I answered too quickly. So loop gain is Kp. So loop gain is Kp over here, and loop gain is going to be half when basically mu is equal to 2, then loop gain is going to be half, right? And because 1 over 2 is 1 over mu, system gain is going to be, so system gain basically says I give a step input, what is the asymptotic output? So this is a decaying term over here. This term over here is a e1 over e to the minus alpha, whatever, doesn't matter. This whole thing is decaying. So that's actually the steady state response to a unit step. So the system gain is going to be 1 over 1 plus alpha mu, and you want this to be a half, which means that mu equals 1 over alpha is going to be the is going to be what you want. Okay, so the system gain is half when mu equals 1 over alpha. Loop gain is going to be half when mu equals 2, and y of t is going to be this part over here. And I think the only tricky part here really is to get the partial fraction properly, but once you get the partial fractions, this is actually pretty straightforward. Okay. And any questions about this?
Sorry.
Yeah.
How do you get the loop gain again?
Loop gain is by definition right here, KPES. So what am I multiplying the error by? So I'm multiplying the error by, sorry, so where am I? R minus y over tau, or mu, I guess in this case. I'm multiplying the error r minus y by mu, right? So that's why I'm getting. I'm using. Let me just use mu everywhere. So that's the loop gain by definition. That's just the definition of loop gain. But system gain is what's the actual gain of the system when you give it a step input and in the steady state. Okay, we saw that in the first order and second order systems, right? We gave it input step and you get the k. That's the system gain. Okay. It's the magnitude of the response. At the end of the day, for proportional mode control, all you really have is Kp. You have the gain parameter, and you tune it. And if you make the gain parameter high, you're going to have responsiveness. If you make it low, you have less responsiveness. So that's basically the bottom line. So the higher the gain, the more rapidly you respond. So let's look at the other mode, which is integral mode. And the first question you want to ask is why? Why bother? Okay. And the integral mode control, the intuitive understanding is that error accumulates. Okay, so the assumption is that error accumulates. If you have a system where there's some kind of energy storage and the error is accumulating, then what you want to respond to is not the instantaneous error value, but you want to respond to the accumulated error, because error is accumulating and you want to respond to the accumulated value. So you're interested not as much as in the current value, but what happened over time, because it could be that you're doing some kind of sampling of the error. You're not getting instantaneous You sample it, and that moment the error was low, okay? But for some reason, the accumulated error was high, and so you want to respond to accumulated error. So the accumulated error is going to be integral of et dt, which in the Laplace domain is going to be e over s. So we want to make u to be proportional to ki integral et dt, which in the Laplace domain we're going to have u equals ki, I stands for integral, over e over s. Okay, so that's the intuition here. The problem with integral mode is it's oscillatory. It causes oscillations. Okay, so you have to be very careful with integral mode control. Okay, if you ever use integral mode control, be prepared for oscillations, and you can pretty much expect them to happen. So we'll choose the gain parameter ki to be small enough so that the oscillations don't happen too frequently. So let's look at the web server again in the integral mode case. And so remember that gs equals 1 over s, and we had over here e equals r minus y, so es equals r minus y, and u equals ki e over s, which is going to be ki r minus y over s. Okay, and so we get y is going to be 1 over s r minus w. That's the plant operating on the error. So r minus w is the net that comes in, and so we can just substitute this to get y equals 1 over s ki r minus y over s minus w. Okay, why are we getting that? Because I just substitute for sorry, not r, u minus w, I'm sorry. Yeah. So this is the command minus the disturbance, which is the service rate. And so we just substitute for u over here, and we get this one over here. And as usual, what we want to do is to compute the step response. So we'll set w to 0, and r equals 1 over s. So let me just gather terms first to say y equals, if you expand this, we get ki r over s square plus ki minus s by s square plus ki w, and so this goes away, and we'll set r equals 1 over s. So if you do that, then the step response, y step, is going to be ki over s times s square plus ki, right? And this can be expanded as y step response is going to be 1 over s minus s over s square plus ki. And again, this works because we get s square plus ki minus s square, which is ki, which is what we have here. So just a simple expansion over here. Generally speaking, whenever we see an s square in the denominator, it's going to be oscillatory. Okay, just like a rule of thumb, because the Laplace transform of cos omega t is 1 over s squared plus omega square, and sin omega t is omega square by s square omega square, or the other way around. I can never keep it straight, but an s square in the denominator is a characteristic that you have for both sinusoidal sine and cosine. So when you see this s square, you say, okay, this is going to be a sinusoid, and sure enough, y of t for a step is going to be, this is just to 1 over s goes to 1, and minus cos square root of ki t, and this is going to be oscillatory with the period of ki. Okay, so if ki is small, it's going to be a small period, and if ki is large, you're going to have a large period. And so this is going to be basically something like this. It's going to be 1 minus this, so this value, largest value is going to be 0, so it's going to be like this. So smallest value is 0, largest value is going to be, so this is going to be the output over here. So if you give it a step input, then the buffer is going to go up and, like a sine wave. Okay. It'll never go below 0, right? We can't have that because it will not go above, in this case, 1. So it's going to, and so you're giving it input of 1 and it's going to do this. Okay. So remember the W is 0. So the server is doing no work, yet we're getting this kind of oscillatory behavior in yt, and yeah, it's because of the integral and the error. Actually, that doesn't make sense now I think about it. W is 0, so
shouldn't the maximum value be 2?
should the maximum value be 2? It's no, when this is 0, then it's 1 minus 0, so that's 1.
And when this is minus 1?
Oh, right. Thanks. You're right, it is going to be 2. When it's minus 1, it's going to go to 2 with the 1. And yeah, sorry. Okay, it's going to be 2. So, I mean, I don't have the exact 0 value properly, I guess, because it's going to be at pi, whatever. I have to think what it means in the real system, because in the real system,
Buffer gets spread over to twice the value of the step input.
yeah, so I guess, but the thing is, it's not getting drained. I'm just wondering where it's draining from, because we're saying there's no draining. So that's, that doesn't seem to make sense. I have to think some more about the physical meaning of this. At least the math is correct. I don't know about the physical meaning over here. So I'm going to think some more about that. So often we are faced with this problem, at least I am faced with this problem, where you do the math, it looks out fine, it's oscillatory, integral mode is supposed to be oscillatory, and then you say, oh, wait a minute, I'm trying to model a web server. What is the web server doing that causes it to oscillate over here? And the thing that's bothering me is that why are we going down in the occupancy, because there's nothing being drained out of it, because W is 0. So I have to see where that's coming from. There might be a mistake, but I'm pretty sure I checked this math carefully. Okay, well, I'm just going to label it as a mystery and move on for the moment.
You have constant input, so
Yeah.
you can vary your rate of processing it. So that
Well, see, remember we said W to 0? So the service rate is W. So I'm not servicing it at all. Yeah?
So you have E equal to R minus Y.
Yeah.
So you're thinking you're only pushing, but if your actual level is going
Above,
R,
yeah.
you actually drain out.
No, I understand that, but then the graph is going to be, it should be always monotone increasing. It should be going like this. Or it's not even going like that. I mean, it should be monotone increasing.
Like you're thinking you're only pushing value.
Yeah.
According to your mathematical model,
Yeah.
you can actually drain value. Drain
When R is less than Y.
Yeah.
Right. But the question is, why would R be? Why would Y be? What you're saying is, if R is less than Y, I should be reducing my rate to drain it, right? That's what the model is saying, because you're saying that the error is R minus Y. Yeah, I get it, but physically that doesn't make sense, because we're always filling it. We're never actually draining it.
Yeah. So this model.
Yeah, this model isn't accurate because it's assuming that we're. Yeah. Okay. I have to think some more about it, and I can't do it in real time. So if anybody has ideas, let me know. But
you can be negative.
beg your pardon? You could what?
U is negative sometimes, so it's less.
Oh, I see. You're going to actually send at a negative rate. Yeah, that would be very cute. That's right. So you're draining it by sending it at a negative rate. You're kind of pulling packets out of the buffer at a negative. But that's only if yt goes below 0. But if you look at the y step, it never goes below 0, right? Oh, that's right. Yt doesn't go below 0, but u of t goes below 0. That's correct. Aha. Okay, I got it. So in this model, we're assuming that you can send packets at a negative rate. Okay. So these, don't be scared. It's not going to hurt you. What a negative packet rate is nothing more than a packet that says drop my packets. Right? You send a packet to the web server saying, look, I sent you too many requests, just drop it. You know, drop 5 requests, drop 3 requests. That's a negative packet, a negative rate. And so if we, in this assumption, we do need to have u to go below 0. Okay, and the way you do it is we need actually r minus y. Yeah, so what we're doing is these the negative packets going out, which is saying remove these requests from the queue. And we're assuming that we can do that over here. And if you do that, you'll get oscillatory system. Okay, we'll never go below 0, but you'll get oscillatory system. And this is actually also widely used in computer networking, but not in this direction, but the other direction, right? When you send packets, you get acknowledgement back. When you get acknowledgement back, you say, okay, I got it. No need for you to deal with it. Just drop it, right? Drop the request because I acknowledged it. So acknowledgement can be viewed as a negative packet. And in the same way, we can have a negative request. So if we want an oscillatory buffer system, you know, and we want to use integral mode control, then we need to allow for negative requests to be sent out, and it will do the job. So yes, so that will work. Physically, or in a real system, you probably don't want to do it, but this is purely for illustrative purposes, and you know, we can do it over here. Dear Kellen, do you have a question? Or? No? Okay. All right. Okay. Let me just spend a moment on derivative mode control, and then we'll probably finish that up next time. Derivative mode control, what we have is that let me just explain what's going on first intuitively. So in derivative mode, what happens is that you want to be sensitive not just to the actual value of the error, but the rate of change of the error. So you, let's say the error is actually increasing very fast. So the error is going up. Even though you're taking control action, you're saying, hey, wait a minute, this is not good. I really want to be responsive, not just to the control, but to the error, but the rate at which it's increasing. So it's getting really bad very quickly. I'd better increase my control. The other way is a bit easier to understand. Let's say the error is dropping. So this is time and this is error. Let's say the error is dropping fast. Okay. Then you say, wait a minute, if the error is dropping fast, I'm probably going to overshoot if I continue with this. Okay. I'd better ease off. Okay. So imagine that you are driving a race car, your target is to get to 220 kilometers an hour, and you know, you step on the accelerator and you go from 0 to 150, 200. When you get to 200, you probably don't want to keep your foot on the pedal. Okay, you want to probably take your foot off the pedal a little bit, because if you keep, of course, error is diminished. It's gone quite a bit, but if you want to go even more than that, you want to take your foot off the pedal even faster than proportional mode, because your error is dropping so fast, you don't want to overshoot it. Again, we're worried about overshoot. Why? Because of delay. Okay, if there were no delay, then we would be fine. You can just use proportional mode. But because there is delay, we are going to be in danger of overshooting by having the error be only be proportional. We want to be sensitive to the rate of change as well. So that's the derivative mode control. The mathematical modeling is very simple. It's just SE. Okay, that's what happens to E over S. So we have multiplied by K derivative. So that's the modeling, and you know, I'll work through the math for the web server next time. The thing to be worried about is noise. So this looks nice and clean, but what if the error looks like this? Okay, right here we have a big problem. We have a very large increase and then a very large decrease. So the derivatives go up very quickly and they go down very quickly. So we're going to have this very, very rapid change in the direction of control, because you go from very large positive to large negative. And so any kind of noise in the error is going to be exaggerated in the control action, and it's probably not a good idea. So what you usually want to do is to use some kind of low pass filtering and remove all of the noise and just sort of smooth it out like this, using that orange curve, for example. And then when you do this, all these high frequency variations go away, and you'll get something that's nicer. So the general rule is when your error accumulates, use integral mode, and when you want to kind of feather in your control and respond quickly when there's a large change in error and you want to take off the control when the error is decreasing rapidly, then you should use derivative mode control. But with integral mode, be careful of oscillation. With derivative mode, be careful of noise spikes. Okay, and there's another issue with derivative mode. We'll talk about that next time. If you read it, please note that there's a typo. In one place I say dE by ds. What it really means is dE by dt. It's in section, just above example 11, it should be dE by dt. And we'll continue with that and advanced concepts next time.